Good morning, everyone. Welcome to our webinar about transforming vehicle architecture, where we'll focus on electrical connections in busbar and PCB applications. We're entirely thrilled to have you with us today. And joining us are our presenters, Dustin Hallenbeck, our Director of Field Engineering, and Nick Marshall, our Global Product Manager of eConnect. The presentation portion of the webinar will last approximately 30 minutes, followed by a question and answer session. So please feel free to type any questions into the chat box as they come to mind. Quick info for everybody, the session is being recorded and we will share the presentation with you afterwards via email. Thanks again for joining, and let's get started. Dustin, handing over to you, the floor is yours.
Thanks, Miriam. So as Miriam mentioned, I'm the Director of Field Engineering for North America. And if you can switch over to that next slide, Miriam. Great, so a brief introduction here. We all know that the EV revolution is currently taking place. We're seeing a dramatic transition from ICE vehicles, internal combustion engine, to electric vehicles. This is giving a major opportunity to most of our OEMs to really redesign the structure of the vehicle itself. One of the major transitions that we're seeing is a cable to bus bar transition for multiple reasons. There's lighter weight, they're more efficient, there's a lot of space savings in specific accesses that we'll talk about a little bit. And with this presentation, we really want to go through a couple of specific PennEngineering categories that are going to be a new product segment known as eConnect. And I'm going to hand it over to Nick here to go through those specific products with us now.
Great, thanks, Dustin. So like Mary mentioned, I'm Nick Marshall. I'm a product manager and my specialty is in these electrical products that we are currently in the process of releasing and bringing into the market in many cases. So one of the big reasons that we are focusing on this segment is that we're seeing with this change from internal combustion engines to EVs, that the power transmission requirements within these vehicles is changing drastically. In a vehicle where previously you were using most of your power in one push to start an engine, and you were using 60, maybe 70 amps for a very short period of time, now we're looking at having to charge batteries, drive large electric motors, and that's requiring 300-400 amps. And in many cases during charging, you're supplying that current continuously for 10, 15, 20 minutes, depending on the vehicle and the charger you're using. Each of these changes is creating a new challenge for vehicle design. We're having to push more and more of this current through the systems that have already been designed. And as the EVs are evolving from first generation to the next generation of vehicles, people are looking for more efficient ways to do this. And the biggest change that we've seen from internal combustion engine vehicles to electric vehicles is the shift to bus bars. And in the world that PennEngineering is most focused on, the bus bar to bus bar connections have been a critical joint. So the focus that we're talking about in a lot of these EV transitions is on the bus bar connections. And the main reason that we are focusing on this is because it's a serious point where losses of the electrical system can happen. We have a lot of power being pushed from one bus bar to the next, and depending on the surface conditions, the plating or the material that the bus bars are coated with, you can see a lot of variation from one bus bar to the next. And so that's where we're really focusing a lot of our efforts with this product line, is on how we get that power transitioned from one component to the next. Miriam, if you could flip to the next slide. So what we're showing here is a product that we've been developing specifically based around this need. This is our eConnect contact bushing, which is designed to create that high current conductive, low resistance joint from bus bar to bus bar. What we're doing with this part is we are using a small copper element that we forge, and then we plate with silver or tin or nickel, depending on the needs of the application, and then we install into the end of the bus bar. When we install this into the bus bar, we have a series of ribs on the bottom of the head that you can see in the animation and in the image in the middle, which pierce into the top surface of that bus bar, breaking any oxidation layers and embedding the conductive element of the bushing into the bus bars. By doing this, we're able to create a very, very low resistance joint between our bushing and our bus bar. And then our bushing is able to serve as the plated contact element on the ends of the bus bar. And the reason that this is important is because if we don't use a component like this, the alternatives are plating the bus bars directly, which can be a very costly and inefficient process, or to use unplated bus bars in a joint where we're really trying to push the power through any oxidation layers or any inconsistencies on that surface. And to illustrate that, we've done quite a bit of testing to show this difference. Miriam, if you could flip to the next slide, please. This shows some of the performance of these different scenarios that we've been talking about. And it's important to note the scale in which we're talking about this resistance to electrical flow. So we're talking about microohms, which is a 10 to the minus sixth measurement of this resistance. So we're on a very, very fine scale. And even at this scale of measurement, we see resistances that can cause damage or can potentially lead to issues like thermal runaway in critical high performance bus bars. If you're pushing for 500 amps through a bus bar and you have 100 microohms of resistance, you'll see significant temperature increases in many cases. And what we're showing on the left here is kind of the illustration of the best case. This is a pure conductor. There's no joint in it. We're just measuring across a predefined distance of 80 millimeters. So this is purely the resistance within the copper on the top image and the aluminum on the bottom image. And with the copper, we're seeing about a 16 microohm resistance, and that's why copper is so commonly used in bus bars. And aluminum, we're seeing 26, which is still a very good measurement, but it's much higher than the copper. However, where we really see the difference is where when we shift to those two middle images, where we're joining the copper to the copper and the aluminum to the aluminum with a bolted joint. And this is pretty typical of what we see in the industry today. These are non-plated bus bars for this illustration, but what we're showing is just the impact that adding that bolted joint can have on the resistance of the connection. So on that, across that same 80 millimeter span, we're going from 16 microohms to 105 in copper, and even more significant in aluminum, we're going from 26 microohms to 397. So that's where it becomes critical that when we make that joint, we are using something that limits the resistance on the surface. And to do that, what we're illustrating on the right is our E-Connect contact bushing. So we've put one in each bus bar, and then we've joined the surfaces of those two bushings together. And immediately you can see that once we add that plated finished surface in between that joint, we bring the resistance back down significantly, back into the range that it was at when you didn't have the joint in between it at all. So we're going from 105 to 20 on the copper and 397 in the aluminum down to 35. So this is kind of illustrating the importance of considering these joints. And we're really focused in PennEngineering on as EVs are changing and as these types of systems and joints are becoming more and more common, how do we create solutions that can enable customers to make these kinds of joints connections throughout the vehicle where it's needed without having issues that could lead to thermal runaway, damage to components that are surrounding this joint, or any other number of issues. So what are some things that we've considered when we're talking about these joints and that we took into consideration with the development of the E-Connect contact bushing? The first item is the current rating of the part, which we're developing our current ratings by evaluating what the temperature change is of the joint as we apply current to it. So we use a couple of different standards that we use to evaluate what the current rating should be of any of these components. And we're finding that within the industry, it's very, very different based on the requirements of our customers or anybody that we're helping use this kind of solution for. So the current rating is really significantly based upon what is the cross-sectional area and what is the material that we are using to carry this current. In the bus bar, the current rating is going to be primarily dependent on the cross-sectional area, which is the area you see as we're looking down the length of this bus bar on the end there. And then when we're looking at the termination where the bus bars are meeting, it's that surface area that in this case is made up by the top of that bushing that's contacting the mating bus bar. And so those two sizes are critical for how much current we're pushing through an application. If we need to carry more and the bus bar is being limited, we can scale up the size of the bus bar. If the bushing is being limited, we can scale up the diameter of the bushing, or we can switch to a different material when we need to. As far as materials go, we have a couple of different options. The two main standards right now in bus bar design are copper and aluminum, and they each have their own benefits and disadvantages. Copper is a fantastic conductor and is capable of moving a lot of power very efficiently without needing a very high volume of it. And the drawbacks are it's very expensive and it's very heavy. So there comes aluminum. Aluminum is not as efficient by volume, but it's much more cost effective and efficient in weight. The difficulty that we have with aluminum, though, is the oxidation layer between bus bars can be much greater and much more of a challenge. So we really worked to figure out what's the best combination that we can give to customers when we're talking about solutions for these terminals. And the eConnect contact bushing is designed to work in both copper and aluminum bus bars. And because it's such a small piece of the total bus bar, we've made it out of a copper alloy that gives you very high current carrying capability and is able to be installed into the aluminum bus bars. So you get that really good joint resistance at the terminal while you get the cost and weight savings for the aluminum bus bars. And when we're talking about how we've chosen to manufacture these, there's two primary options for manufacturing with these materials. We can either machine them or we can form them into the final shape. In low volumes, the machining is very attractive because we can quickly set up and we can run a small number of parts. But when we get into the larger volumes, it's really, especially in these high value conductors, much more efficient to form them. And the reason for that is when we don't have to cut away that valuable material, we save money and we save on the cost for production because we don't have to waste anything. When we're forming it, we're using this original material and we are just reshaping it into what we finally need. Then the last item that we've really considered when we're talking about these joints is the platings we're using. Gold and silver are some of the best platings that we can use. They have a very low contact resistance and they do not tarnish very easily, making them very reliable in the long term. Nickel and tin are also great for this purpose. They don't provide the same level that gold and silver do, but they give you a more cost-efficient solution. And so with the eConnect contact bushing, one of the benefits that we've found is we can manipulate which plating we apply to this bushing, and we can put it into any standard bus bar depending on what the needs are for the application. If you have a very high service life, very critical junction, it's probably more effective to go with the silver plating where you're going to get that tarnish resistance and that ultra low contact resistance. But in many cases where you're not going to be looking at a very long lifespan, or it's not a very long time between manufacture and assembly, we can often get away with something like tin, which still gives you that very good contact resistance, but it's a much more cost-effective option. Miriam, could you flip to the next slide, please? So now talking about some other ways that we've been looking at these terminals. The one we've discussed previously in the contact bushing is meant for bolted connections in bus bar to bus bar connections. What we've also been developing is a clinching pin and a clinching socket, which can be installed for quick connections between different bus bars. Typically or traditionally, a lot of these types of joints have been done using off-the-shelf headers or multi-piece assembled connections that are fantastic for their versatility, but not so efficient when you're looking at a customized design or something with very strict requirements. And that's really where we've tried to take some of our expertise in the forming and manufacturing of fasteners and make some simpler, but still very high performance solutions that could be used in more optimized or more customized applications where some of those off-the-shelf parts don't work as well. So with the eConnect pen, what we're doing is we're taking a brass silver-plated pen and we are clinching that into a bus bar, or we're broaching it into the top surface of the PCB. So we're removing the need for additional loose hardware or for assembly steps for other headers, and we're pressing this directly into the bus bar where it's permanently captivated into that joint. Then we're doing the same thing on the other side, where we've developed the socket that you see in the top right, which has a series of coiled connective points, which are making the joint between that pin and the mating bus bar. Because that's coiled and those coils are laid over top of each other, they interference fit with the outside of that pin on multiple different points, giving you a large contact area in combination and making it flexible to be slipped over the pin without any extra force or steps. So this is kind of the way we're trying to move some of our solutions in the future, of providing the efficiency that customers have been using in designs that have been around for a while with a simplified geometry or a simplified attachment method to make the total assembly and the total production of these systems and these applications that the customers are trying to put into larger modules a lot easier and a lot more straightforward. So this next slide is kind of a bit of a look at where we're trying to go in the next round of development. On the left, you can see what we're calling our copper SMTSO, which are surface mount fasteners for PCBs, where we're plating these in tin or silver or gold, and then they're getting resoldered directly onto the surface of the PCB during the reflow process that attaches other components. The benefit of this is it's an easier assembly and an easier manufacturing process for a lot of PCB manufacturers. And what we're trying to do is take some of these lessons learned from our other eConnect products and apply them to the PCB world. We initially started with busbar to busbar connections, where we were trying to make those simple joints from one conductor to the other. But we're seeing increasingly that customers need to join those bus bars or those other systems to additional components like PCBs or wiring harnesses, whatever it may be. And so they need a solution similar to what we've developed for bus bars for those applications. And that's where the SMT would come in, is when you're trying to create a joint or a terminal that can apply that current to some of these larger electronic circuits that we see, this is an option for that. And then on the right, what you're seeing is our no hole required voltage sensing pin. So this one's earlier in development, but what it is a pin that can be pressed directly into the surface of a bus bar. And then a terminal crimp clip or slip-on clip can be attached to that, and it can be used as a checkpoint for sensing the voltage and monitoring the system that is connected to that bus bar. If we're talking about a battery management system, this becomes crucial, because to monitor the health of that battery, you need to know what kind of current or what kind of voltage is being passed through at any given time and what the resistance is of the system. Typically, this has been done with bolted-on connection systems or welded tabs that can be connected to sensors. And so we're trying to, again, take some of those lessons learned of the attachment methods we use in other systems and apply them in these new ways. So now I want to talk a little bit of the testing that we've done in this area that goes a little bit above and beyond what we've done in traditional mechanical fasteners. So for all of our eConnect products, we've been focused on what is going to be the long-term effect of putting these in an application. You know, when you're talking about a high performance joint that's used to power an EV, the performance of it, not just when it's assembled, but also 100,000 miles down the road, is critical. And it takes a different level of testing that we've really been looking into, been investigating and committing to. There's a couple of different standards that we found that approach this. US CAR 2, LV214. A lot of them are designed around wire connectors or cable connectors, but we've adapted them in many cases to bus bars. So some of this testing that we've done in specific is we've really focused on current cycling. What is the performance of the conductor as we put it through 1,000 cycles of 45 minutes at 500 amps and then 45 minutes off? how does that affect the resistance and the integrity of the joint? We've done the same with temperature and humidity and thermal shock. If we take this joint and we raise it up to 125 degrees and then we quickly cool it down to -45, does that thermal expansion and contraction cause any issues? Does the increased humidity promote any oxide growths that we weren't expecting? And we've found it's very important to our customers to understand this. When we show this data, it really is something that needs to be discussed when we're first introducing the product and we're first discussing how we validate this, because the customer is going to expect that they're going to have to do the same level of validation on their joints. And if they're using our products and we're talking about a single joint, how can we confirm that we aren't going to be a single point of failure in these large joints? And these tests are really helping us do that. We've also added 4-wire micro-ohmmeter testing and 3,000 amp power sources to each of our test labs in the US and in Europe. And we've been conducting vibration testing on the mechanical side to evaluate the reliability of these joints. And we're proud to say that on all the parts we've tested thus far, we've never had any issues with these joints. Everything that's in our catalog that we stand behind, we can show what these results were. We can show the testing standard that we tested this to. And in many cases, what we're finding is as we're doing this testing, the joint will hold up. This vibration test was a great example that you can see in the bottom right corner. After 24 hours of continuous vibration, the joint with the bolt, the nut, and the 2 bushings performed exactly the same before and after. And during continuous continuity monitoring, we saw no issues. But actually, the bus bars themselves, where they're joined to the testing rig, would fail in fatigue. So it speaks to how important the design of the whole system is in ensuring that the electrical joint will be consistent. But it also speaks to how, when we're looking at the reliability of our parts, we're really focusing on not being the weakest link in the system. We want to outperform the other components that we're connecting with.
Okay, so to summarize everything that Nick has talked about, and we've gone through this presentation, really want to address, kind of go back to why someone would go through eConnect. First and foremost, electromechanical joining, having those within one space. PennEngineering over the past few years, it's been very apparent that more people want to shove more stuff into a smaller space. So being able to take your mechanical joints and combine them with your electrical joints, giving you more room, more space to be able to do things, is really critical in a lot of these applications. Next, as well as installation optimization. Between both our Hager and PEM Certer brands, we're able to provide an insertion solution no matter what your volume, your application is, whether you need something that's in die, inline operation, or offline. We're able to provide an insertion solution for every single one of these products where we can confidently say, whatever your application is and whatever fastener choice you go with, we're going to be able to install that part for you with one of our in-house solutions. And then really kind of the biggest advantage of all of this is the removal of the platings, right? You can always silver plate your bus bars, but including those outside operations and the costliness of having to send out bus bars for silver plating is extremely cost beneficial to transition to an individual fastener of the same plating solutions. The other really benefit here that we can talk about as well is transitioning from future solution proofing. And what I mean by that is we've seen a large transition of customers transitioning from copper bus bars to aluminum bus bars in future steady state application types. And with this fastening solution, you're able to use the same fastener across bus bar based materials, which means you can future proof a lot of your designs for your next generation of product. And then all the testing that Nick mentioned here, we're able to do those on application by application basis. So if you do have specific parameters or a specific application that you would like for us to review, we're happily able to do that for you depending on what your specific parameters are. We have quite a bit of our traditional clinch testing in-house, but we do also have vendors that we're able to work with to provide a lot of the kind of above and beyond testing solutions that are required by our customer base. And then the last one here that I want to talk about as well is our global footprint as PennEngineering and as PEM, where we have design engineering efforts wherever your design engineering efforts are. If it's in North America, if it's in Europe or Asia, we have specific engineering teams that are local that are able to support you on site wherever you are. On top of that, also with our global production capability of where we're able to produce. So we can really follow your design and application anywhere around the globe. And I believe at this time, Miriam, we're also ready to take any questions and anything from the group.
Yes, you're right, Dustin. That brings us to the end of the presentation. I hope everybody found that insightful and relevant. And as I mentioned earlier, we're happy to share the presentation with you and also provide samples of the eConnect contact bushing on request to you. And we have had a couple of questions in. If I just kick us off with one, I don't know, Nick, whether you want to take this. There's been a question about whether there's an industry standard for bus bars and bus bar connections at all.
Sure. So there's not a true industry standard for all bus bars and all bus bar connections. There are some industry standards that we use as references that have been developed for other connections or that reference bus bar connections. LV214 and USCAR2, like I mentioned, we've used for testing. UL 1099 and 2148 both also reference bus bar connections. But there isn't truly a specific standard that we found in our literature reviews that tell us explicitly how to make these joints. There are some trends in industry emerging. We're seeing that bus bars are typically falling within the range of 2 to 6 millimeters in thickness on the upper end for aluminum and on the smaller end for copper. And we've really sized a lot of our products around those requirements. Speaking with our customers, working on the development that they have both currently and in their pipeline, we're trying to see where the industry is going and where it's going to land on a lot of this stuff. We expect that eventually much of this will be standardized, but right now it's a lot of combination between what customers have asked us specifically and references in existing standards.
Okay, great. I suppose that's leading into that. There's been a question about wanting to join a copper bus bar to an aluminium or aluminum bus bar. What is the solution there? Could you comment on that?
Yeah. So this has been a long-standing issue as people have been transitioning from copper to aluminum bus bars. Really making that connection is most difficult because of the oxidation layers. And that's why we've turned our focus from PennEngineering into creating solutions that can bridge this gap. The eConnect bushing is specifically designed to mitigate those oxidation issues, and the eConnect pin and socket are meant to bridge that gap without the contact of the two bus bars themselves.
Okay, great. Nick, could you answer the question about how the eConnect contact bushing's electrical resistance is compared to welded bus bars?
That would very, very much depend on the specific welding that we're talking about. There's a great number of welding options that are being used in the industry right now. There is ultrasonic welding, resistance welding, friction welding, and each of them have a different resistance value corresponding to them. In general, we find that our resistance values are on the low end of what you'll find with welding and are more consistent from joint to joint. On a purely numbers basis, we tend to sit around 5 microohms across the joint on a bushing to bushing connection. And that is comparable to the low end of welding that we've come across. The difference is we see a very small variation in that 5 microohm value, whereas in welding, we've had customers come to us with issues where that variation is much larger.
Great. Nick, there's been a question about the current rating limits for each contact point. Is that too specific? If we're getting too specific, maybe we'll reach out separately.
Yeah, we can follow up with testing data. It's very dependent on the size of the contact point we're talking about. Our standard eConnect bushing in an M6 size carries about 400 amps of current with a sub 20 degree Celsius temperature rise. As we scale that up, that current rating increases. As we scale it down, it will decrease.
Okay, now we're getting some quite specific questions. So I've got one which is more general as well. Somebody's asked what's the best material for bus bars? Is it copper? Is it aluminum, sorry, again, or something else?
So in previous years and traditionally, the choice has always been copper. It gives you the best middle ground between cost for the bus bar and performance. But we're seeing a transition in the future where aluminum is becoming the better choice. It's been limited in its application because of that more resistive oxidation layer, but there's an increasing number of solutions similar to our contact bushing and our PEN that mitigate that issue. And as that issue is resolved, the aluminum bus bars are becoming much, much more appealing.
And let's pick another one. Dustin, feel free to jump in if you see any questions that pique your interest.
Yeah, Nick, we have one here that's is it required for there to be a E-connect bushing on both sides of the bus bar connections, or can you use just one within a joint?
That is a function of what the mating bus bar type is. If we're talking about a bus bar where you're using the bushing on one side and the mating bus bar is an unplated aluminum bus bar, we would strongly recommend using two bushings. If the mating bus bar is already a silver plated contact terminal, then it's probably not necessary. It depends on what the resistance and the service condition of the mating bus bar is and what the requirements are for your joint.
Question about availability of materials of the contact bushings. What options are available?
So we make the contact bushing from a C14415 copper alloy. It's a lightly alloyed copper, giving us about 88% of the current carrying capability of C110 pure copper alloys. And that's really the recommended copper alloy for this bushing because it provides the best combination of hardness needed to penetrate those ribs and conductivity for the joint.
So there's a question also about whether the E-connect bushing has teeth or knurls on the other side to dig into the mating part and whether that's necessary.
The standard part does not. And the reason for that is because you would be relying on the assembly of the second panel to drive those teeth in. And in many cases, people aren't putting enough clamp load on the mating fasteners to drive those teeth in. It can be done. We've developed concepts in the past for double-sided bushings in specific applications. But for the standard part, we're using a flat surface where we can provide the best contact area with that plating to make contact with whatever the pre-prepared surface is on the other side.
Okay, great. And with the testing, was there any galvanic corrosion buildup on aluminium and on the copper during the course of the testing?
In the testing that we did according to US CAR 2, we didn't observe any significant corrosion between the bus bar and the bushing itself. The bus bars and the bushings individually, particularly the unplated section of the bus bar that was used as the test component, would corrode, but the surface finish that was prepared on the bushing did not, and that was the important portion for our test. Now, we have taken it a step further in some customer-specific testing and done salt spray and salt fog testing where we submerge the bus bars in a chamber, expose them to accelerated aging, and then do the testing. And that's obviously developed some galvanic corrosion over time, but we've seen that the performance of the contact bushing or the pin doesn't degrade with that change in age and weathering exposure.
And I believe to clarify that one as well, Miriam, they were talking with aluminum to copper connections, which in most of our cases, we have some form of protective plating, as Nick mentioned, either the silver, the tin, nickel, or gold platings within those. So we kind of use that as a mitigation layer between them to keep their galvanic variance avoided between them.
Great. Great. Okay. I'm not sure if there's any, Dustin, if there's any other questions that you have. Let me just scroll through.
I see a question about can we share the performance data and the testing data? We can do that, absolutely. We can also schedule a review if you have some specific questions with our outside applications team that would be happy to walk through it with you and show kind of what we did, how we arranged it, why the data is reported the way it is, kind of just give you that background.
Fantastic. And any specific questions that have come up on the chat that we haven't answered, we're more than happy to reach out. There is these are the contact details for Nick and Dustin. We will share the presentation with you and follow up in an email. and maybe that's the right way to continue and go from there. So at this point, we'd like it to thank everybody. Nick, if there's anything you want to add as closing up, or Dustin, otherwise we'll wrap it up.
The only thing I will add in closing is, because we have quite a few very specific questions here, feel free to shoot those over to us. We have an outside sales team that would be happy to help you with the specifics of this and any individual design or special cases where we can discuss what the exact performance of this part would be for you.
Great. So thanks for everybody's time, and I hope to connect with you soon.